a bigger audience than what I had at AGU. So this is, it was early, I had an 8 o'clock presentation, so this is...
Don't take it personally.
So this is nice. So, as Dr. Burton mentioned, I'll be talking about sort of these hydrogeochemistry variations in 2 mangrove ecotones. I like to recognize sort of my funding sources through the Florida Coastal Everglades long-term ecological research, as well as NASA for funding this research. So to jump right in, why are we looking at coastal mangroves, so these coastal wetlands, and why is water so important? So this is sort of a generalized water budget for the world. And what I'd like to really draw your attention in is looking at the total evapotranspiration coming off of terrestrial land and what's coming off of these wetlands. You can see that it's really small, but when we sort of look at it sort of per unit area, I'll direct your attention here to this green box. So we have forest and woodlands, we have wetlands, and then we have these subtropical and tropical wetlands. And it's a smaller sort of land surface coverage, but a higher release of water into the atmosphere. So we can see this ratio here, this much larger than any of the other biomes. And because of this, how is it affecting the water budget when we change these environments because of the loss of mangroves? So again, why is like ET and rainfall recycling so important? Is in these subtropical and tropical wetlands, we can actually have ET rates higher than precipitation. ET is essentially evaporation from open water bodies plus the transpiration, so from photosynthesis of vegetation. So in the cases of subtropical wetlands, we can actually see, and what I'll show you here is this is time here on the x-axis. We have millimeters per day for rain and evapotranspiration and sort of the cumulative totals. And you can see over time, from 2007 to 2008, we actually have more ET happening over the course of precipitation. So there's more output through ET than there is input through precipitation. And because of this, you can actually have some rainfall recycling. And what we've seen in the Amazon is about 35 to 50% of evaporation is actually recycled in rainfall. So water vapor comes up, it gets condensed, and comes right back down. And I can direct you here. So this is the Amazon. Essentially, if you have 100% precipitation, 75 coming in, you have this sort of 25% loop. In the Amazon, we have similar here in the Mississippi Delta, and in the Everglades, we have about 7 to 12% that's recycled. So if we look at mangroves and where they are, and then look at population densities, and this map didn't really come out too well, but here the orange highlights are where mangroves exist. The dots are coastal populations in excess of 1 million people. So you can see that along these sort of mangrove ecotones, we have a high population, increasing populations in these coastal zones. So what does this have, what impact does it have on the degradation of mangroves, and what will this have on the influence of the water budget in these coastal zones? So just to give you a little background on sort of the loss of mangroves, we've had about a decline of about 35% over the past 20 years. This is worldwide. And this comes out to about 2% per year loss of mangroves. And I'll just sort of direct you to this table down here. Again, so this is about 35% over the past 20 years, coming up to about 2% annually per year. And what we've seen in the Everglades is actually sort of a landward migration with sea level intrusion, or saltwater intrusion, sea level rise. We've actually seen a migration of mangroves inland about 1.5 kilometers. And again, because of the altered hydrology that Nusha mentioned earlier, as well as saltwater intrusion. So what implications does this have on the ecosystem as well as the water cycle for the Everglades? So the objective of this research was to essentially calculate spatial estimates of ET across different mangrove communities and correlate these measurements with water quality and water availability. So essentially my first hypothesis is to look at the reflectance values, and I'll get into more of that later, of mangroves, and see if there's any, the reflectance value should change with changing or variations in water chemistry and water availability. The amount of water released to the atmosphere from ET in the mangrove ecotone is going to be influenced by the seasonal water quality, because as they're stressed, they're going to transpire less. The dwarf mangroves will have a lower ET rate than the taller mangroves, and this is because they're, or is hypothesized because they're in more stress conditions. That's why they're smaller. Siancán, which we showed earlier, I'll get a little more detail, and the Everglades, in their coastal zones will have similar correlations between these hydrogeologic conditions and their spectral responses because of their similar vegetation, similar climate, and similar subsurface conditions. So here we have the Gulf of Mexico, Florida, and Mexico. Here we have the Everglades. I'm not really going to go into much of this, but we do have Shark River Slough, which is sort of the main conduit of water that delivers water to the Gulf of Mexico. And I have 3 sites that I'll get into more later. Taylor River, it's sort of the smaller conduit, delivers water directly into Florida Bay. And then we have the Siancán site. We have 2 sites here, the Playón site and Rio Negro, and I'll get into more of that in the next few slides. So I won't give much of this, and we'll go kind of fast through the Everglades geology, but essentially we have alternating layers of carbonates and siliciclastics, and this is sort of comprising the superficial aquifer system, the Biscayne aquifer, and these are very transmissive formations with hydraulic conductivities ranging between 1.5 and 4.5 million meters per year. And then all of this is sort of overlain by a thickening sequence of peat as you go seaward. So now switching over to Siancán and the Yucatan, again it's composed of these sort of similar layers of highly permeable limestones, sandstones, as well as a few evaporite sequences. They have an extensive karstic system in the sense of underwater caves. I think it's the largest in the world with their underwater cave system, and these sort of cenotes, which are their local sinkholes that connect you directly from the surface to these deep underwater cave systems. As well, we have the nearby Chicxulub impact crater, which you can actually see the fault zone right here on the northern end of the Yucatan. And there's also some fault zones associated with this that we can see here in this paper from Gondway et al. And these are sort of his proposed faults because we see sort of continuous groundwater discharge in sort of these areas along these proposed fault zones. So you guys know sort of the climate here. We have a nice warm climate, high precipitation in excess of 1 meter per year. And you guys know the wet season, dry season, that most of this happens between the months of May and October. The annual ET can exceed the amount of precipitation, hence making this sort of an important study to look at. This ends up ranging between 2.6 and about 7 millimeters per day. And you know of our frequent tropical storms, even though we haven't had one recently.
Say that.
And again, Siancán, almost the exact same statistics. A little bit higher mean temperature. Again, sort of a variable precipitation. Their network for measuring rain and ET isn't as extensive as ours, so their ranges are much more broad. But again, over a meter, depending on some years. Again, they're wet season, most of the rain. Again, ET, there's very few estimates of ET, but they range between 40 and 85%. It might be more. Again, their ET estimates aren't that extensive. As well as I see frequent tropical storms. So this is Rio Negro here, and these are pentenes, which are their sort of local tree islands, and these are all dwarf mangroves here along the river. So we'll bring you back to Shark River and to sort of show you the sites that I have. So these are the mangrove ecotones. If we remember sort of Shark River coming down, we have SRS 4, 5, and 6. They're populated by red, black, and white mangroves. Excuse me. At each of these sites, I have 3 stations, short perpendicular transect here. We have groundwater wells, deep groundwater wells at SRS-6 and SRS-4. And then each of these I'm collecting pore water from 20 centimeters, and that should actually read 85 centimeters from some paired sippers that I deploy at each station. We measured water level and groundwater at each of the sites, and we have a nice eddy covariance tower, which you can almost see right here in this picture at SRS-6. And then we go to Taylor River, a completely different environment in the sense of the size of the mangroves. If you look at Shark River, these mangroves are in maybe excess of 30 meters, 20 meters, and I'm taller than these mangroves. So you can see a really big difference between the two. We have two sites, TS6 and 7. Again, it's a sort of a salinity gradient. These are predominantly red mangroves. We have, again, groundwater wells. We collect pore water, surface water. We have a weather station, which you can see here. And again, we collect surface water levels and groundwater levels. So now to bring you over to Sian Khan, we have the Blyone site, which is right here. There's a road sort of similar to what we see in the Everglades, or yes, along 8th Street. There's an impacted zone to the south, which you can see here, with groundwater salinities in excess of 50 PSU. And then we have sort of the more pristine Rio Negro site to the south, down here. And again, we see sort of the typical what we see here in Taylor River. We've installed groundwater wells. We are going back again in May to hopefully install some more, take some more samples. And they have a few weather towers in the area. So I sort of mentioned some of the sampling scheme sort of already is, you know, collecting surface water, collecting groundwater, collecting pore water to depth, and running all of these for major ions, chloride, sulfide, excuse me, sulfate, potassium, magnesium, calcium, and sodium. Run this for major nutrients, so nitrogen, phosphorus, and TOC. And again, running stable isotopes on these, we can sort of pinpoint different sources. Again, we have water level, we have local meteorology. And then I also collect this spectra, which is, I'll get into more of that later, which actually the sort of reflected energy that comes off of mangrove leaves. And we can use these changes in that reflectance to actually measure stress conditions within the mangroves. And this is done, one with a handheld unit, and then we can actually bring these sort of up to satellite acquisitions where we have Landsat, which sort of just came offline, so it's going to be a little difficult with that, but also EO1 Hyperion, which is a hyperspectral satellite, and then try to get images from every season. This is sort of up to a whole bunch more images. So the idea of stable isotopes, you can pick out different sources of water. Rainwater will have their sort of signature stable isotope of deuterium oxygen. Surface water will have a particular signature, and so will groundwater. And you can actually tease this out if you were to take stem water samples, because it's been shown that there's no fractionation in oxygen as a plant sort of takes up water. And you can actually look at and create sort of a mixing line where you can look at how much water is coming from a particular zone. How much of this tree is sucking water up from groundwater or from the surface water. So this goes with the field collections. We'll be collecting leaf and canopy, or I've been collecting leaf and canopy level measurements, and sort of going from the field leaf level, site level scale, and bring that up to get to a regional scale where we can sort of make these broad estimates that are going to be more cost effective than these really pricey site-specific measurements that we have to make. So here's a little bit of the theory actually behind the reflectance and using spectroscopy in this. Here we have wavelength on the x, this is in micrometers, and sort of energy here on the y-axis. And what I'll point out is here is blue, green, and red. This is visible light right here. Blue light, green light, and red light. So this dotted line here, actually I'll do this dark line, is actually what the energy coming from the sun outside of the atmosphere. And this sort of darker line, or this line down here, with all these sort of dips in the sort of absorption features, or what happens is the energy coming through the atmosphere. So we see most of the energy is in the visible light, which makes it benefit for us because that's where most of the energy what we can see. But we can actually use this relationship to measure changes in the intensity of the reflection from the vegetation. So directive here, again we have wavelength, again we have blue, green, and red light. This is a typical signature that we'll see from typical leaf, typical vegetation signature, where we have, this is reflectance, where we have absorption in the blue and absorption in the red, relatively higher reflectance in the green, why we see plants as green, right? And then this sort of really high near-infrared reflectance, which is what we can't see, but this is related to water content, cellular structures within the actual leaf. And this will change depending on water chemistry or other stress-related conditions. Kind of went over that. Again, so the visible absorption is related to chlorophylls, carotenoids, xanthophylls. And then we can see changes due to nutrient water stress. So you can see in this study here is, so these are all typical reflectance signatures. Again, you have absorption in the red, reflectance in the green, high near-infrared reflectance. But when we add, this is sulfide to the equation, it actually drops. This is a sort of a stress condition for the, in this case, corn. So it's actually dropping the near-infrared reflectance. So we can actually measure that and make some estimates based off of that. So this is actually the machine that I take out in the field. It's essentially a gun that you really just hold up to the vegetation, and this is what it measures. Again, what I've just been showing you, again, wavelength, reflectance, we have red, green, blue, green, and red. And these are for the 3 different mangrove species. So I measure these for 5 sunlit leaves with 3 replicates of each species at each station. And you can use certain ratios of these, different wave band ratios, to calculate these particular indices. So a typical one is NDVI, where NDVI is sort of based off of the near-infrared reflection and the absorption of the red. So these are just a suite of biophysical indices that you can calculate, that you can use to compare against water chemistry, temperature changes. Many of these studies have shown a whole bunch of different relationships with these particular biophysical indices. And now to bring it up to the satellite level, to get us a bigger footprint of what's going on, we can use Landsat 5TM, which is a multispectral satellite. It has 6 bands and 1 temperature band. And what we can see, this is the same image using 3 different band combinations to kind of tease out different information. So this is sort of natural color. This is a false color infrared, and another sort of false color infrared. And the bands are sort of related to different wavelengths. And then we also have the Hyperion, which is another satellite. This is a typical image you would get. But this has 242 bands. So you can actually get a better sort of signature. Again, here's your sort of your typical vegetation signature. High infrared reflectance and your green reflectance. So you can get a lot more information. Again, this is 242 bands versus 6 bands. So these are sort of average, and this is sort of a higher spectral resolution. And with these sort of spectral changes that you get, you can actually calculate ET based off of remote sensing. And it's mainly through this energy balance equation. Essentially what's coming in, so this net radiation, so the incoming minus outgoing gives you net radiation. And then, so net radiation minus sensible heat flux, sort of heat that's used to change the temperature, and groundwater, or sorry, soil heat flux, which is energy used to heat the soil. That difference equals this latent heat of evaporation, which is the energy needed to transfer states. So to transfer from water to vapor, and that is essentially what's the evapotranspiration term. And this is sort of a model I built up. I know this is a little busy, but essentially we'll start with the original atmospherically, well, the original image directly from the USGS website. We do an atmospheric correction, and we can get, this is temperature that comes directly from the image. We can calculate albedo, we can calculate a particular vegetation indices, and this gets us, we can calculate net radiation, we can calculate soil heat flux. We put it into this, the energy balance equation, and it can come out to ET in millimeters per day. No worries. So this is sort of the model that I've been working with. I mean, there's still some tweaking and some more stuff to work on. But you guys will see more of that stuff at the forum. And then again, doing some sort of spatial and temporal analysis. These are some preliminary results. I'm not going to go into this. You guys have to come to the forum to hear more. But essentially, we can see relationships between the spectral indices here on the Y and pore water concentrations at, again, this should read 85 and 20 centimeters. And again, these are the biophysical indices used from the site-specific data. So then, part of this is actually looking at how things change with space and how they change through time. So here are, again, more Landsat images. This is NDVI. So we can see changes through the year. This is 1993, and it goes all the way to 2009. And essentially, you can see these changes, be it because of hurricanes. It's 1993. This is after Andrew. I'm not sure what this one's after, but this is after Wilma and Katrina. So you can see some changes related to that. But what do these changes have on evapotranspiration? What do they have on changes in water chemistry? And can we use these changes through time to actually look at typical, or to look at sea level rise that we've kind of seen in Shark River, where we see sort of, this is salinity here on this black dotted line. So an increase in salinity at Shark River, and a relatively, a relative increase in at Taylor River. So can we sort of tease that out using Landsat images? So some of the preliminary results, I'm just going to mention them. Again, you have to come to the forum to get more information. We were able to use mangrove leaf spectra to estimate ionic concentrations in the pore water and surface water at both the field scale and the satellite scale. All the mangroves, regardless of species or type, it being tall or dwarf, showed similar responses in their spectra with increasing ionic concentrations. This is something else which is down here, which is the satellite data from multiple years was actually able to, or we could model typical water chemistry dynamics within the Everglades, again using satellite data from multiple years. And that's what we see here. You'll get more of this at the forum. Essentially, this is chloride concentrations through the year. So this is January, getting into the late dry season, we see an increase in chloride concentrations, and then this is sort of the end of the wet season where we see lower concentrations. This is from Taylor River, this is Shark River. You sort of see the difference between the two. And sort of a plug, myself and a few other graduate students are hosting and organizing the International Space Apps Challenge. This will be April 22nd and 21st at the Engineering Center. A little background on this. President Obama, just last year, started this sort of open government partnership to sort of increase the amount of transparency within governments, sort of the collaboration between governments and participation. So NASA actually developed this International Space Apps Challenge as a way to kind of make this collaboration happen. And it has come to now almost 25 locations that are going to be holding this event all at the same time, including the International Space Station and a NASA base here in Antarctica. And excuse me, so this will be all going on that same weekend. And so essentially what this works, or how it works, is there's a list of challenges, a list of global challenges, and teams will get together and they'll actually develop a smartphone app, some kind of application to address these challenges. And these will be teams of you know, ranging in age from high school to professionals, from coders, computer scientists, engineers, smartphone enthusiasts. I mean, whoever wants to sort of get into this and sort of help make a difference in the sense of, you know, collaboration, open source. I mean, these apps would essentially be made from publicly available data. So anybody can essentially do this, and this is a global collaboration where participants at the Miami event will actually get to communicate with people in Australia, people in Germany, and talk about all these ideas and talk about these challenges. Just quickly through the benefits, again, we're talking about this open partnership, kind of this collaboration, get citizens involved in the sense of space exploration, and to get them involved with, you know, with these people that have little or no investment in that, and to see how important it is, not only space exploration, but the sense of NASA doing all kind of science, earth science and space science. Again, promoting STEM, encouragement of this international partnership and mutual understanding, and as well as demonstrating the open government partnership. Don't worry about that, it's just an agenda. So here's some nice pictures. This is from Sian Khan. This is the Everglades in the dry season from last year, dried down completely. This is Shark River, and this is from the cold snap that we had a couple of years back, that is actually still growing back here. You can see more effects of the cold snap in Shark River. This is one of the tree islands in Sian Khan, and this is within that tree island. This is actually taking a picture from right there in those mangroves. And with that, I'll end with any questions.
Wasn't a cold snap, it went on for 2 weeks. It's a mini ice age.
Yes. It was actually 2. I think it was 2 cold snaps.
Do we have any